Hi everyone, this is a short video to present the questions about Laplacian equation. For question 1, the figure Q1 shows an experimental setup involving two parallel conductor plates with surface area S. The plates are separated by a distance d and they are connected to a DC supply. The S marks indicates the special region between the two parallel conductor plates. For part A, we have to set a suitable assumption regarding the dimension of S and D so that the electric field within region S could be approximated to that of the infinite surface charge. The answer for this question is the electric field inside region S could be approximated to that of the infinite surface charge where the dimension of S is greater than D. For part B, we have to determine the direction of the electric field within region X. The direction of the electric field is in y direction. It is determined by the polarity of DC supply. The electric field is directed outward from the plate having the more positive potential in accordance with the equation of vector E equal to negative gradient of vector V. So in this question, the DC supply is connected in y direction. That is why the electric field is in y direction.
Explain the act of stipple diagram, the microscopic effect of the electric field in a dielectric material posited in the X region. When there is no electric field applied, the positive charge is surrounded by the negative charge, as you can see in the diagram, so there is no electric field applied. So next, when electric field is applied, the charge cloud is distorted. As you can see here, when we apply electric field over here, so all the negative charge it will be accumulated here, and the positive charge will be go away from the negative charge. So this phenomenon can be reduced to a simple dipole using the superposition principle. Since there is a distance between positive charge and negative charge, we can say that there is a dipole moment which is P equal to QD. As a conclusion, the major effect of electric field on the dielectric material is a creation of a dipole moment that align themselves in the direction of E.
The question 2 is give us the coaxial capacitor structure where shown in the figure Q2. And this capacitor have a length of L and the inner radius is equals to alpha and the outer radius is equals to beta. And the gap between the two conductor is filled with a homogeneous charge-free dielectric material with the electrical permittivity epsilon. And the outer conductor is grounded and the inner conductor is kept at a constant potential of PO. And then the next slide will show how we get the capacitance. So from this diagram we can see that the changes is only the radius. So we can get the Laplace equation in the cylindrical coordinate is equals to this equation. And then we let it equals to 0 and we integrate it, we will get V equals to ln R plus B. And then from this diagram, we can see that when R equals to beta, the V is equals to 0 since the surface is grounded. So we substitute this R and V into the equation 1, we will get V equals to negative ln beta. Then we substitute B into the equation 1, we will get V equals to ln R per beta. Then when R equals to alpha, the V is equals to VO. So we substitute this alpha and VO into the equation 3, we will get A equals to VO over ln alpha per beta. Then we substitute equation 4 into the equation 3, we will get V equals to VO ln R per beta over ln alpha per beta. Then E is equals to negative del V, also equals to negative dV dr in the direction of R. So we differentiate this equation and substitute into this equation, we will get E equals to negative VO over R ln alpha per beta in direction of R. Then Q is equals to integration d dot ds. As we know, d is equals to epsilon E. So we substitute E into this equation and we know that ds in this surface is equals to R d phi dz in the direction of R. So we solve this equation and we can get the Q is equals to negative 2 pi epsilon L VO over ln alpha per beta. Then C is equals to Q over VO. So we substitute this Q into this equation and then solve it. We can get C is equals to 2 pi epsilon L over ln beta over alpha.
For question 2BA, to determine a suitable dielectric material that will produce a capacitance of 5 picofarad to 10 picofarad, we will use the formula C equals to 2 pi epsilon L over ln beta over alpha to determine the capacitance of each material listed in table Q2. So after calculation, among strontium, barium, tantalum, and mica, tantalum is the most suitable dielectric material, with capacitance C equals to 6.836 picofarad.
Next is question 2b. This question asks to find maximum voltage, maximum charge, and also maximum energy for the dielectric material that has been chosen in question 2b1. Okay, to find VO max, we rearrange the electric field formula E equal to negative V naught over R ln alpha over beta. We get VO max equal to E max times R ln beta over alpha. We choose tantalum for the dielectric material, so the E max is equal to 10 power of 5. We substitute the value into the formula and we get VO max equal to 109.86 kV. Okay, next, to find maximum charge, we use formula Q max equal to negative 2 pi epsilon L V naught over ln alpha over beta. We substitute the value into the formula. Q max equal to 2 pi times 8.854 times 10 power of negative 12 times 27, because we choose tantalum before, so the dielectric constant is 27, times 5 times 10 power of negative 3 times 109.86 K divided by ln 3 over 1. So Q max equal to 751.03 nanocoulomb. So for the max energy, we use WE max equal to 1 over 2 QV. We use the value for the Q and V from the maximum voltage and maximum charge and substitute into the formula. So we get WE max equals to 41.25 millijoule.
For the resistance of the capacitor, we will use the formula R equals to epsilon over sigma times the capacitance, and we will get the answer 3.497 times 10 to the power of 14 ohm. That's all from our group. Thank you for your listening.